after you've uploaded your data into the visualizer, note that you can do Control, and then if you're using a mouse, you can use the scroll pad to zoom in and out, depending on what size you want. I do recommend for this process, where we're going to be annotating compounds, to have 2 monitors. So one monitor, you'll have your FluoroMatch Visualizer, and in the other monitor, you'll have your data table. So you'll open up your visualizer and upload all your files into it, as we showed in the prior tutorial, and then go back to your outputs and also open up, for example, the neg ID fin table. So either positive ID fin, neg ID fin, or combined ID fin, depending on how you're looking at your data. So let's say you just ran negative polarity, open up neg ID fin, and you'll get your table. And here we're going to be using Office Libre, or LibreOffice, I should say, which is like an open source version similar to Excel. You can also, of course, use Excel or whatever spreadsheet software you want to use. So these are the results. And so I'm going to keep, as far as what I'm going to be looking at, I probably want to know the formula, series score. Definitely want the identifier and the series type to look at, but I'm going to be hiding a bunch of other columns. So let's hide this one. We want our MZ retention time, and then I'll probably hide the rest of the columns until we get to the end here, and then we want to keep our checked viz and the columns thereafter. And I'll show you why in a second, because those are the ones that we're going to be using to annotate. All right, so let's see how this looks. So this looks good. Now we have all of the information we need. And so let's look at our visualizer. And the way that I like to annotate the compounds is to go from the top of your sheet downwards, because the way that FluoroMatch provides this sheet is it provides the most confident series based on various metrics at the top, and then goes down to lesser and lesser confident series. So if we start at the top, we'll get the easiest series to look through, and then we can keep moving our way downwards. So this check viz means that I've looked over a series. So let's look at 16, series 16. So I'm going to pull out in the series column over here, series 16. And so you can just type in series 16, select it, and now you'll see series 16. Note that our scoring was on, so I'll want to take our scoring filters off. So I clicked the select all twice until they're all white boxes. And that way, in case there's other scores within that series, we can see everything within the series and validate. So in this case, we have very nice trend lines for our compounds. And you can see, even though these are C+, for example, this first one, it still falls nicely within the homologous series. And then you can see a number of A's. So again, A's have less than 5% false positive rate, highly confident, and so I would consider this a very confident series. If you wanted, though, you could, look through a few of them. I usually, when I'm trying to confirm members of a series so that I can confirm the entire series, because really we only need to know that one's confidently assigned, and generally speaking, the rest of the series that falls within that trend is going to be that same type of compound, same PFAS subclass. So here I would click one of the members of the series that's lowest, and we can look just if you wanted to validate it. Again, if they're A's, often they're highly confident, but it's still good to be able to get a feel for whether they're real or not. So one is the formula prediction is correct. Formula prediction can be false, and you can still have the true compound because it's only using isotopic pattern and mass. You might see the correct formula in one of the top 10s. You may not even see it, but you can at least see what the isotopic pattern looks like, and then the theoretical over here versus actual. You can see it. Darker blue is predicted, lighter blue is experimental, and then here's the isotopic pattern that's just from your MS1 data as well as any other MS1 scans. So in this case, we have a clean MS1 data. Often I'll zoom in just on that peak for the MS1 here. Let's see. And you can see that there's not many other peaks in the MS1 spectra, so that is good. Along the 1 Dalton around the molecule. So this fragmentation is pure. It's mostly belonging to the ion that we're looking at. The isotopic pattern's good. You will see, if we select over here, you can see the percentage of sulfur will usually be about 4%. So if we look, okay, there's sulfur at 4.47%. So usually we won't see a very big N+2 and definitely not a similar sized N+2 to our N+1 unless we have sulfurs. And then it even gets larger if we have 2 sulfurs. So this isotopic pattern in both of these show that it's likely to contain sulfur. The isotopic pattern is the only one in the accurate mass that actually matches. The only formula given is for the sulfonic acid species for C4. If we look over here, the formulas are actually for the sulfonic acid species based on MSMS evidence because it's a score A, and so we get the same formula. So both of these are giving us the same evidence, and then we can look at the MSMS, and indeed there you see the precursor ion. We see SO3F, SO3, and SO2F, and so we do have lots of sulfonic acid related fragmentation, and so we can be quite confident that this is the species. And so again, I wouldn't go one by one through all of the species in a series necessarily, unless you only have a few species identified, such as plasma or blood, and you want to be confident in every one. But in the case of this AFFF contaminated soil, that would take too long. So I've just looked at one. It looks very good. And I also know it has an A, so I've already been confident. So I can be confident in all the members of this series being correct. They all follow a nice trend line. The other thing to look at here is isomers and whether they're real or not. So I'm going to shift and click to drag over 2 of these isomers. They're isomers because this y-axis is retention time. So you have 2 of the same mass, the x-axis is mass, with different retention times. So here we can see indeed 2 peaks. So we would expect 2 isomers, and you can just double check in this table. One's 5.03, which is right here, and the other is 5.22, which is right here. Great. So these isomers are real. And so then we want to just click really quickly through to make sure that there are isomers for all these. There's again 2 peaks. This one has 4, so that's the question, is there actually 4 peaks? And I see 1, 2. It also says that there's one at 7.43, so let's zoom down and see if there is a peak. So probably just tailing. There is one at 7.15, but the 7.43 is probably incorrect, probably just a tail of this species, as you can see. And so now we can look at our table, and let's make sure we ground ourselves. So we're up to C8 for the formula already, and the one we're trying to get rid of is 7.43. So we can go to checked viz. First, I'd also freeze panes. So, I believe. Let's see. Oh, here we go. More used to Excel. All right, so it's freeze pane. So now you can scroll down. So our checked, we'll just say that we checked all the sulfonic acids because by the end of, when we're done, we're going to have checked all the sulfonic acids. So we want all those to be 1. So it's just to say that we checked it. Note that you can put whatever you want in these boxes. I just put checked as 1 or 0. But you can have different values, especially for the true viz. So this is, can be your confidence score. You could even put a Chabernet scale here, whatever you want to put. I usually put 1 as true, 0 as false, and then sometimes I'll have like 0.5 as maybe. I need to look back at it. And then there's a comment section as well, right? So you can put comments in. So for the true viz, in this case, we know that they were all true. They all followed the nice trend line. Those isomers were real until our C8. And then it was the 7.42 that was incorrect. So I'll put a 0 there. And the rest were true. So let's drag that up here as well. All right, and then now we got to keep looking, right? So let's keep looking. So again, all of these I'd be confident in. I just want to make sure that these isomers are real and not tailing, like we kind of saw in the last one. So make sure that if you need to see other peaks, so for example, this one's missing. Sometimes you can just click a nearby neighbor, even though it's a different mass of charge. So I'm clicking nearby neighbor. I know that this neon green is not the one. So it does look like there's a bunch of isomers here. The only 2 that were shown for C9 were 7.44, which is actually this species over here, which is good. And then 7.6, which is over here. So I actually missed this species. Either that wasn't picked or the mass might be slightly off. So sometimes you can have missing species as well. And so if you want to make sure that you have everything, you can note that as well. But I'm not going to note that. I'm just going to assume, okay, both of these are correct. Same thing. Let's go series to series. Okay. Again, 8.22, 8.05. Okay. Again, there could have been more isomers here. Note that when you do have more samples, in this case we only uploaded a single sample, and so it only has a single chance to find all of those peaks, that it will have more chance of finding all those isomers. So again, I'm just clicking through and making sure that at least those isomers are correct. There may be more isomers as we've been seeing, but I just want to make sure that the ones that it is identifying that we may do statistics for, etc., are correct. So 9.18 would be this one, 9.05 would be this one, and 8.97 would be this one. So again, could be all correct isomers. So I'm going to be happy with the rest of them. Of course, there are some judgment calls for what you want to consider real or not. These isomers are generally going to be branched isomers, and also because you may not have MSMS for all of them, if they fall out of that retention time range to too large an extent, they might actually be something else that's not a PFAS. But they all seem to fall within that trend line nicely. And so now we'll go through our carboxylic acids in the same way, and then you would look through your ethers, so on and so forth. So I'm going to skip the carboxylic acids because we won't annotate an entire database today. That would be a long video to watch. And I think these ethers might be a little more interesting. So let's look at them. They're series 12. So for the next series, we're going to go over here, click 12, select that, unselect our 16. Note that I selected the 12 first and then unselected the 16. The reason is if you unselect all series with all scores unselected, everything's going to load into memory at once because you've unselected everything. So you'll have all your data show up, and that can slow down the software. So now here's our series. Looks very good. This data, the AFFF contaminated soil, this is actually NIST C from a PFAS interlab. And this data looks way better than you should expect your data to look like. So don't, just because you don't have these nice series and as many compounds annotated in your data set, even if it's AFFF, don't worry. This is an exceptionally nice data set with, or as far as the complexity of the PFAS within the data. So if you have blood or something, you might only have one or two series and they might be pretty sparse. This might be a much harder process, but I am giving you this example. So again, the trends are nice. Did want to show one thing here, which is here's an ether species. Let's again, look at the lowest one. It can often be easier to confirm. So if I click this species, here's a peak. It's actually pretty low in abundance. Here's your isotopic pattern. So again, in this case, it didn't get the right formula for any of the top 10, and yet, this may be some noisy, pretty low MS1 spectra, and it's okay. The isotopic pattern looks decent for what I'd expect for this ether species, so even though the formula prediction didn't get it, I'm not worried. What I'm most importantly focused on is this MSMS spectra. So we do see an SO3F, right? And our species, if we scroll over, is a sulfonic species, so we do expect to see SO3F. And we also do have an ether linkage. In this case, it says the ether linkage is right next to the CF3, because that oxygen could be anywhere along that chain. So what fragments do I see? I actually see C3F7O at higher abundance than CF3O. And then I see C2F50 as well. So there's multiple isomers here where that oxygen is linked to the rest of the chain. So actually, when we see the species, even though it's saying OCF3, that oxygen should actually be in the main isomer. Not one position over would be OC2F5, and 2 positions over would be OC3F7. So it actually, the oxygen should be two positions over to the left. And so we can put that into our notes if we wanted to know the exact isomers. In this case, I won't, just for time's sake, and it just depends on the time and the depth you want to go in. You could actually say, okay, we do know what the predominant isomers, and actually know that there are actually, even though we are only seeing one peak really here, there are multiple ether linkages that occur in the species, and so the species actually is 1, 2, 3, 4 species, not one. Same thing, if we look over here, we're probably going to see a couple of different ether linkages. And you can see that this peak is a little bit wide, potentially. Again, I'll also look with the isomers. Yes, indeed, here's 2 very widely separated isomers. If we look at the fragmentation in this case, in the case with the sulfonic acids, we couldn't see any difference in the fragmentation for the isomers, so I didn't look at it. But with the ethers, we can tell the position, right? So CF3O is the predominant for one, whereas C4F9O is the predominant for the other. So you can see that there's 2 isomers here, same thing. Over here, we can click through. C2F50 is the predominant. And in this case, it's also C2F50. So that's an interesting case where there could either be branching or there's other isomers mixed in and they're shifting where that peak height is. which there definitely are other isomers. So with that, there's definitely two isomers in all cases. They all have good fragmentation. Again, you probably won't see fragmentation for all of yours. This is an ideal data set. And you can also look at the overall profile to see the kind of isomer distribution. And often you'll see in homologous series, not always, that you get similar peak shapes in homologous series. Actually, the PSA homologous series, the peak shape looks very different than these ethers. And so in this case, they're all correct. So I'm going to go into our ethers, and I'm going to drag down. I've checked all of them for 12, and they're all true. All right. So you would continue this process. Obviously, you wouldn't have skipped the carboxylic acid. You'd just keep going down. The question I often get is, when do you stop? And that's really up to you when you stop looking down this sheet. So you can see in this case, there's lots of A's and B pluses and C's. So there's a lot of confident hits. And so it might take me a while to get to 138 here. Annotations. And so I'd look through all of the series for sure that have B pluses and A's because these have really nice structures that we can be fairly confident in, especially the A's and the B pluses have a good starting point. After that, such as the B minuses and things like that, you might want to stop, or you could look carefully through those. And you can keep going. So the D pluses may be nice homologous series. They have no MSMS evidence, so the question is, are they real? But you don't know what their structure is going to be. Some might have formula prediction, but most probably won't. And then, you could keep going down. So in our case, especially with something so rich in PFAS, I might stop here at the B minuses. But if I had more time, I could do D pluses. If you are in blood or something, you might have very little A's or no A's, very little B pluses, or even no B pluses. Rare, but possible. In which case, you may have no PFAS in your sample. You might have detected something with your sensitivity and what type of matrix you have. But you also could have to look at some of these lower confidence. So let's just look at a lower confidence species. So let's start with this B minus, just to kind of walk through how you would look through a lower confidence. So this has no homologous series. It's feature 1072. This CF2N0 needs no homologous series. So if you try to look at the 0 series, it's actually going to show you everything that doesn't have an homologous series. So that's not helpful to pull it out. We need the 1072. So if I then go over to here to features, and I go to 1072, note that it won't show up until I take off this series. So this might be one of those cases where you might want to put another filter. But again, in our case, software is probably quite quick. Well, talk too soon. Here it goes loading. All right. So there's the 1072. So you just have to be patient in that case. So here's the species. No MSMS that we see here. It did get a B minus, and remember that means that it did have MSMS information. But the way that our MSMS spectra, and this may change in future versions, so this may not be an issue in future versions, is compiled here is that if there's more than one MSMS spectra, more than one feature for a specific MSMS spectra, the feature with the closest retention time is assigned that MSMS spectra. So when you have overlapping molecules, we can look at the isotopic pattern. So we do get this nice isotopic pattern. It does look almost like, so if we look here, the chlorine, we expect about a 32% peak. So indeed, this is a chlorinated species. Does have this kind of chlorinated look to it based on MSMS. It got a C8 chlorinated species with sulfonic acid. We do not see, here we go. Yeah, so that C8 species is within the formula prediction, so we can look at how well that matched. Not bad, actually. You can see what that distribution would have looked like for a single chlorinated species. So definitely one chlorine. Most likely it is the species because it's a common species. We can also, even though you don't see the fragments in the MSMS spectra, you can scroll to the right here. And you can see what fragments it saw. So it saw the sulfonic acid and the C2F4 sulfonic acid. So we know it has a chlorine. Let's look at the structure over here. So we know it has a chlorine. We know that it has a sulfonic acid and a part of that chain. So I'd be fairly confident that this is the correct species. I would assign this a 1. Again, we don't know where the position of the chlorine is on this chain, but it's probably not at the terminus because we do have a C2F4SO3, right? So this would have a chlorine in it. If it was a fragment, it might be next to that if that's making this cleave more easily. You can also see there are 2 isomers here. So even though it only pulled out 1, right? So it is missing some peaks as we've noticed in a couple instances. So we can go over here and again, right, just like we would previously, 1 and 1. You could, if you wanted, because the MSMS is not as clear as you might want it and the formula prediction, you could give this a lower score. I'm fairly confident, but again, you know, this is more a user choice depending on what you're doing. If you're doing regulatory work and you're going to do a lawsuit based on the occurrence of this chemical, you're probably going to want to buy a standard and confirm it. You're definitely going to want to buy a standard and confirm it, right? You're not going to want to just use non-target analysis. So in the end, if you want 100% confirmation, you'll need to buy that chemical standard. So let's also look at a D. So in this case, the series number would just be 31. So this is going to be the same exact thing we did before as far as looking through other compounds. Because we have 1072 selected, it's not going to show us that one. So now we have to wait again, right, for it to load. You can see all the rich series within this region here. So let's pull out series 31. All right, so this is a D+. It's got a really nice mass defect, pretty close to this line over here, meaning that it's mostly fluorinated, and maybe has some other, and you can see some fragmentation actually over here, even though it didn't get a fragment assigned, so not exactly sure what's going on there as far as giving it a D+, and you can see these very nice EICs. So it looks like there was an error in the software in terms of the score here, because we do see some fragmentation. And we can kind of click through. So this says a C6F5, which is kind of strange. You'd usually see a C6F13 or at least a little more Fs than C6F5. Same thing for the C7F11. You usually see C7F15. So either highly unsaturated species, or it could be a ringed species or a ring. These are just some ideas. But again, it's a little difficult. You know, you could use CFMID or other in silico to try to get ideas for this structure. It could be an in-source fragment or a dimer. Does have a very high mass. Does have a very high M+1 as well for a PFAS species. These fragments, again, quite confident in terms of being PFAS-related fragments. And then the series is clearly a homologous series. This is a good example because we haven't seen previously where things fall out of the homologous series. So in this case, I'd be very confident that this one over here, the gray, which makes it difficult, is a false positive, right? It doesn't fall within the homologous series. I would also consider this a false positive, although depending on your chromatography, it can form, we would need the other dots along it. Something else you can do to try to add confidence in whether something's a member of a series or not is take a series that you know is confident and overlay it. So for example, if we go to our table, we knew the PFSA series was confident, so we can scroll up to the top. That's 16, and we can overlay that. So let's take 16. And now we can see, what those series look like. And indeed, it doesn't look like this would fall within that series over here. You can see how this helps extend your logic of how the chromatographic gradient is and how the series should look. So in the end, I would throw out, you can shift click even if you want, highlight these. So it would be, and then we can scroll to the left over here. 2, 3, 4, 7, and 1, 2, 4, 5. So again, scroll all the way down because we start with some D's just to show you how to do that. And 1, 2, 4, 5. So it was just these first two, right? We can double check that. Oops. But instead of true vis, we're going to put false vis, right? So put a 0 there. Now these other ones, we could give a 1. I'm confident they're PFAS. Or, you can write whatever you want. So in this case, I'm going to put PFAS. So in this case, I could put known. Or I could put, 0.5, meaning, yeah, it's a PFAS, but, or let's do a 0.9, right? Because 0.5 could be your maybes. 0.9 is, it's a PFAS, but I don't know what the structure is. So you can come up with your own naming system as long as you know what you're doing. And so we've checked all the members of the series, and the rest are also correct. Again, we don't know what they are. We just know that they are PFAS, because that trend, especially with that mass defect and that trend being so clear, I have no questions. And then with the fragments on top of that, there's no doubt, especially those low mass fragments like C2F5 and CF3, that these are PFAS. All right, so now I'm going to show you, we went through and we've added some. Of course, you would finish this entire sheet, right, up to the point where you want to stop and look through everything. But I'll show you what we can do now. So save this as, we probably should have saved it as something else before we started annotating it, so you don't mess with the original sheet. Otherwise, you have to re-upload. So every time that you annotate this, so let's say we saved it now, we wanted to look at the results in the visualizer, and we uploaded them, and then we wanted to continue annotating and look at the results in the visualizer again, we need a new name. So you could do annotated 1, annotated 2, annotated 3. Just the way the visualizer works. So then we close this. And then the way to pull in that data that we have, I'm going to unselect everything. So now this should be, well, and 30, 31, 2, let's see. All right, so now there's all the scores, all the data. And then we go to, again, that transform data. Remember how we got our data originally. And we'll select that, go to data source settings, and we're going to go to neg ID thin. That's the only one we're going to need to change. All the other ones are linked. And then we're going to find our annotated one. There it is. Press open, OK, close. And as long as you didn't mess with any of the column names, you can't change any of the column names, things like that, then this should load totally fine and relatively quickly. Because the only thing now it has to load is the neg ID fin. The ones that take a while. So again, the Kaufman appended that occurs oftenly, just close that and click apply again. The only ones that take a long time to load are the MS1 spectra, the EICs, the MSMS, because those can be. So it should look exactly the same when you load it in. It's the same data, but now if you look at these flags, you can see the different flags, right? So I can often, how I'll use this is I'll say, I actually want to look at the things that I haven't checked yet. And start looking through those for new compounds, right? I don't want to keep annotating the same thing, look through fragment screening, try to find unknowns, and then all of a sudden end up with the same compound. So that's one way you can look at it. Another way is when you finally finish your data set, then you can say, hey, I just want to show those confirmed PFAS. So I can just click this. And then, you can use this for publication figures. When you distribute this Power BI, you can distribute it actually online. And that can be really powerful too. And then you can have these flags available so that users who see your data set online can see what you confirmed, what you didn't confirm, and they can look for more unknowns as well. You do need a Power BI paid account to distribute this online as an HTML embedded link, but we have an account that we can use for you. And we do host the data sets as well. So for example, if you go to innovative-omics.com and you go to data sets, you can see all of the distributed data sets over here, right? So here's some Revident, so Agilent Revident, NIST C, so the same type of data we were just looking for. They can open it up like this in full screen. And then we can also, when you're in this full screen mode, you can see these flags. You see that I released it already with certain isomers, certain flags already distributed with the data set so people can see which ones you've annotated. And this is a great way to release it with a publication. So please do email me your data sets so that I can host them on this database of all these interactive data sets. And of course, with it, you can put your manuscript if you want. You can put any acknowledgments, the authors, so on and so forth with this data set. Because it's just a web link, you can put whatever you want to be like. You can have links to your own website, so on and so forth. With that, I'd like to thank you for watching this tutorial. Happy annotating of your data sets. And please do send your data sets over. Let me know if you get really cool results. I always love to hear what kind of new PFAS discoveries are being made. We'll also have separate tutorials that you'll find in this tutorial list going over the entire Power BI framework. So, we didn't discuss how to do the Kaufman filtering or all of these filters over here, how to do fragment screening, looking at the Kaufman plots. So there's a lot more to look at. We didn't really talk about what a homologous series is here in depth if you're not familiar with these plots. And so all of those are shown in that previous tutorial video. So please look at that video, and then now you know how to annotate compounds using all of the evidence and bringing those annotations in.